Hello students, welcome to this course Power Quality EE 5260 for this semester Jan-May 2021. This course is mainly for PG students, that is the Ph.D. and MTech dual degree plus BTech students in the final year or in the third year who have done power electronics and power system course. The course is basically in slot E, as you can see from the display, and the days are Tuesday, Wednesday and Thursday. The timings are 11, 10 and 8, and the Friday class is 4:50. Friday class I will take once in a 2 week to address your problems, queries and questions based on the lectures discussed. The course structure is also mentioned here. It consists of basically 6 units, and the 7th unit is combination of 5th and 6th, which comprises of basically the power quality introduction, and the second unit is single phase circuits, discussing about the power definitions, components and properties. Similarly for 3-phase systems, and the fourth handles the fundamental theory of load compensation, which describes how to compensate a 3-phase unbalanced load with purely reactive network. The 5th one is about the shunt active power filters used to compensate unbalanced and nonlinear load. And the 6th unit is about series compensation using the series power filter, series active filter, which is called a dynamic voltage restorer. The 7th one is basically UPQC, Unified Power Quality Conditioner. I will describe details of these devices in the next presentation, after this presentation. Now these are the reference books that you may follow. Mainly I will follow the first book, the NPTEL web course on power quality and power distribution system. This is the NPTEL book written by me, and I will upload its latest version on the Moodle that you can go through. You can also refer the other books to enhance your knowledge, broaden your views on the subject and solve various problems. The marks structure is like this. There will be mid Qs of 25 marks, and then you will have assignment and seminar about 25 marks, and then in-term exam about 50 marks. Your attendance should be greater than 85% in the class through Google Meet. I hope it is clear, all the points. Now we will start some introduction on the power quality that we will go through in this course. The term power quality has a different meaning to different people. In the context of power system, we have 3 main components of our system, that is the generation system, transmission system and distribution system. If you look from generation point of view, power quality may mean that the generator is not overrated in terms of the real and reactive power. It is not overheated, it is well protected against the faults. For transmission side, it means that the more transmission efficiency, less outage, proper flow of active and reactive power, balanced and sinusoidal quantities over the transmission network. And for the distribution side, it means that there must be a rated voltage at all distribution buses, and load harmonics should not be present, should not be propagated towards the transmission side. The power factor should be close to unity in order not to create the threat to the utility, etc. In general, we can say that power quality means the balanced and sinusoidal waveform of voltage at rated frequency in power generation, transmission and distribution. However, it has many aspects, and to cover these aspects, the following issues or problems are being classified. So, the broad classification for power quality can be in terms of these parameters, such as transients, short duration variations, long duration variations, voltage unbalance, and waveform distortions, voltage fluctuations, power frequency variations. These are some of them. So let us look at transient. As you know, the transient in power system refers the events which are undesirable and momentary in nature, and as the time passes, their magnitude disappear. It basically describes the part of the variable that disappears during transition from one steady state to the another state. Again, the meaning of transients varies in the context of the power system. For example, for utility engineers, they view transient as surge from the lightning strokes. For what the surge resistors are used to protect. Switching transients. For the end users on distribution side, transient anything is referred as anything unusual that might be observed on the power supply, ranging from the voltage sag, swells to interruptions. Okay, and these transients are broadly classified into three main categories, and these are impulsive transients, oscillatory transients, and the multiple transients. You can see it here. Okay. So this is the impulsive transient and oscillatory transient and multiple transient. Their names are enough to give you idea what they do mean. For example, impulsive transient, it definitely have an impulse, a huge magnitude over a small period of time, such as lightning strokes come under impulsive transients. Similarly, oscillatory, where there are oscillations in the system, and multiple transients, where there is a multiple strike of the transients. Current chopping, such as current chopping, repetitive switching patterns, and so on and so on. Okay. So now we will study one by one and see how they are being defined and what is their consequences, how do they arise. Now if we see the impulsive transient, as I said, that this is the transient which has higher magnitude for a small period of time. So it can be defined as the sudden and non-power frequency change in the steady state condition of the voltage or current, or both, with unidirectional polarity, either positive or negative. And it is characterized by the rise and decay times which can be revealed by dominant frequency in their spectral content. For example, if we say that we have 1.2 50 2000 impulsive transient, okay, so 1.2 cross 50 microsecond cross, you can say, if you want to put it here, cross, then 200 volt implies that this transient goes from 0 to its peak value in 1.2 microsecond, and then it decays to the half value in next 50 microsecond. Now these transients are mostly damped by the resistive circuit elements and do not propagate far from their source. The most common cause for this impulsive transient is basically lightning. Okay, this figure gives you idea about what an impulsive transient looks like. You can see it here that the magnitude is quite high for a small period of time. This point, actually, if you look, and then it decays almost exponentially, and these impulsive transients travel over some distance along the utility. In the process, they can excite some natural frequency of the power system, may produce oscillatory transient response. So let us come to the term oscillatory transients. As the name indicates, that it is having oscillations. Therefore, it is characterized by a sudden and non-power frequency change. Okay, by sudden and non-power frequency change. In the steady state condition of the voltage or current, positive or negative, because these are oscillations, so they may have positive or negative magnitudes. These transients are natural transients and therefore frequently occur than the impulsive transients. These transients can be further classified in three other categories. They are called high frequency transient, and then medium frequency transient, and the low frequency transient. Okay, and these frequency ranges are defined like this, that for the frequency more than 500 kilohertz, okay, we will get the high frequency oscillatory transients. And for those which are less than 500 kilohertz, they will be called as medium frequency oscillatory transients. And those below 5 kilohertz are called as low frequency transients. Some examples are shown on the right side of the figure. As you can see, that the first one is oscillatory transient caused by back-to-back capacitor switching. So we have basically capacitor switching in the system, and that brings the oscillations in the system at very high frequency. The next two examples are low frequency transient because of the capacitor bank energization and because of the ferroresonance phenomena in unloaded transformer. Okay, these cause the low frequency transients. So the frequency, as you can see, the frequency of oscillation depend upon many factors actually. That is the configuration of the network, the parameters of the transmission line, the feeder and nearby grounding. So many aspects are there. Then the next classification in the beginning that I have shown was the short duration voltage variations. These short duration voltage variations are caused by fault conditions in the network, energization of large loads which require high starting current, intermittent loose connections, and these conditions create the short-term variations in the voltage, causing temporary voltage drop known as voltage sag and temporary voltage rise known as voltage swell, and temporary loss of the voltage known as voltage interruptions. Now there are standard definitions of these terms. For example, voltage sag is defined as the voltage decrease of RMS value of the voltage from 0.1 to 0.9 at power frequency for a duration from half cycle to 1 minute. These voltage sags are normally caused by energization of heavy loads, the starting of large rating induction motor or any other load. You can see it here that in this particular figure there is a voltage drop. You can see from here to here. Okay, this is this period, and this is shown also in the time waveform from here to here. So percentage change is from 20% has gone the change. Reduction in voltage is almost 20% of the available voltage, and then slowly it rises to its normal value after few cycles. The same thing is shown here. Okay, initially it was 100%, then it comes to a very low value, and then it goes to the normal value. There are two different situations. This is for motor starting, and this is for single line to ground fault. This example will clear the point. Suppose we have an induction motor of very high rating, that is the 50 horsepower 3-phase induction motor, and is supplied by a feeder of 100 kVA 120 amps with a 5% reactance. Now initially the current is 860 amp, while the rated value of current is 120 amp, but initial current is 860 amps, which is almost 7 times of the rated value. and this will cause the drop because of the reactance, 5% reactance here. Okay, so this reactance will cause the drop of this much, which is around 25.3%. Okay, and that tells us that there will be reduction of voltage at the terminal of the induction motor as almost 25.3% reduction. So the available voltage will be 75% only. And this may create the problem for the other loads connected to that bus. Okay. Now then comes voltage swell. Similar to voltage sag, there is a voltage swell. However, in voltage swell, the magnitude of voltage increases from 1.1 to 1.8 at the fundamental frequency or the power frequency for the period from half cycle to 1 minute. They are not as common as voltage sag, and they are normally caused by the fault conditions, switching of heavy loads and the energization of the capacitor banks. Now, just to indicate what it is, you can see from this figure that we have the voltage sag here, voltage swell here, which goes to almost 15% rise, max value, 115 means 15% rise. You can see this is the rise, and again comes back to the normal value here. Okay. This may be also caused by single line to ground fault in case of the ungrounded system. In ungrounded system, when one phase is connected to the ground due to the ground fault, then the other phases becomes the line to line voltage, which are high voltage. Okay. So in ungrounded system, the other phase voltages may reach to 1.73 per unit if one phase takes fault to the ground. One phase is connected to the ground. Okay. And the voltage interruption is basically the non-availability of the voltage. So when the magnitude is less than 0.1 per unit for a period of 1 minute, then it is defined as voltage interruption. It's normally caused by power system fault, equipment failures, and control malfunctioning. And these are usually measured by their durations, because magnitude is almost close to 0, less than 0.1 per unit. Okay. Now this is example of the voltage interruption here. You can see for almost 30 cycles it was off from here to here, you can see, and this is in terms of the timing diagram. So for about 2.3 seconds the voltage was close to 0. This may be caused because of delayed re-closing of the protective devices, okay, and or because of the faults in the system. These may also be preceded by the voltage sag when these interruptions are due to the faults on the source systems. There is a further classification in terms of timing. For example, here you can see I have discussed earlier that half cycle to 1 minute. Now this is quite long time in terms of transient. So what happens between half cycle to 1 minute? So this time scale is further classified into three categories. One is 0.5, the half cycle to 30 cycles, then 30 cycle to 3 seconds, and then 3 seconds to 1 minute. And they are termed as instantaneous, momentary, and temporary. Okay, instantaneous, momentary, and temporary. The definition for magnitude almost remains same, as you can see here. Okay, this is point 1, and then we have 0.9, this is 1.8, this is 1.4, this is 1.2. So the upper limit is changing and other values remain same. That is in case of the voltage sag. It becomes 1.8 for a momentary instantaneous, 1.4 for momentary, and 1.2 for temporary. Having said that, there is another kind of parameter that is called long duration voltage variation. A long duration voltage variation are termed as under voltage and over voltage and sustained interruption in the system. As far as the magnitude is concerned, the criteria is same, but the time scale is different. The time scale is that the more than 1 minute. Earlier we were talking about half cycle to 1 minute, now it is more than 1 minute. So voltage, over voltage is any voltage more than 1.1 per unit existing more than 1 minute. Similarly, under voltage is a voltage less than 0.9 more than 1 minute at power frequency, and long interruptions are the interruptions where we get 0 voltage for more than 1 minute. Okay, so it is the time scale that makes either over voltage or voltage swell, under voltage or voltage sag, long interruptions, or you can say simply interruption. Got it clear, this point? All right. The next important classification was voltage imbalance. This is another power quality aspect that has to be looked in three-phase system. As you know, the three-phase system is being designed to operate for balanced load currents and fundamental frequency. However, with increasing the load patterns, load variations, the nature of unbalance is more, and the presence of harmonics is also there. So these voltage imbalance or voltage unbalance has to be measured to indicate that how much the system has unbalance. Okay, these may cause because of asymmetry of load current, the geometric arrangement of transmission lines, and the mutual interactions. Also, the major source of voltage unbalance or imbalance is single phase loading or unequal loading on the phases. These are normally characterized by the symmetrical components, zero sequence, positive sequence, negative sequence. So we transform them into the positive, negative and zero sequence components, and then we define a parameter called unbalance factor. Here you can see unbalance factor and unbalance factor for negative sequence, unbalance factor for zero sequence. Now as you see that these unbalance factors basically characterize their corresponding component. For example, Ku0 is Ba0 by Va1. So Ba0 is zero sequence voltage A phase divided by positive sequence voltage A phase. This is showing the variation of this voltage unbalance over a period of week, and it shows that how the voltage in the supply may vary from almost close to go to maximum 2.5 to 3% unbalance, which is very common. Even if you see in our supply or at your home, then you will find close to 3% or 4% unbalance. You could easily observe it. Okay. More than 5% voltage unbalance variations becomes threat to the operation of the motors. They start humming, they start rotating at some variable speed, causing problem to the load and so on. Okay, so the significant unbalance in the system has to be avoided at any cost. The next point was the waveform distortion. The waveform distortion can be further categorized by these parameters, like DC offset. You can think of DC offset. Then in terms of the harmonics, then we have interharmonics, notching and noise. There still could be many more, but we are talking about here very important parameters. The DC offset may present in the system because of the DC current, which may be coming from single half wave rectification here. This may also be caused by the source side effect. For example, if the source voltage itself has a DC component, this may come from geomagnetic disturbance at higher latitudes. As you know, Earth is a magnet, a big huge magnet, big size. So when transmission lines are being erected and carrying the electricity at high latitudes, okay, there is some effect on the transmission lines, and this causes induction of some voltage, which creates a DC component. But mostly there is very small component from the source side, but mostly the DC component comes from half wave rectification from the load side. And the other things that may cause the DC component is like electrolytic erosion of grounding electrodes and other connectors. Okay. Transformer saturation may also be affected by the presence of the DC component. So they have a very detrimental effect on the functioning of the electrical machines and transformers, because the presence of DC component may lead to the saturation of their core. And then comes the harmonics. As you know, harmonics are the multiple integer of the fundamental frequency. Okay, they are the multiples of the power frequency, or integer multiples of the power frequency. These harmonics originate mostly because of the polytonic based loads. And these are being characterized by their magnitude and the phase angle at certain frequency. There are certain parameters which are used to denote the or quantify the harmonics, like THD, called total harmonic distortion, or sometimes it is TDD, total demand distortion. Okay. Now, what are the consequences? What are the sources of harmonics first? So, these sources could be a saturated DC, saturated core of the device of the transformer or machine, which operates around knee point. This creates the flatness in the voltage with third harmonic and fifth harmonic. Okay. And the polytonic based devices, converters, which are very frequently used nowadays in all the applications at home and office, creates the very high magnitudes of these harmonics. They include the EPS, SMPS, TV, printers, LED devices, the track-based fan. Nowadays, in our office and in our home, we almost use electronic power converters inside them. This is an example of the ASD, called adjustable speed drive, which uses a polytonic converter to control the speed of the drive. So you can see here the nature of current is having basically very rich in third and fifth harmonic, and this current flows through the feeder and it causes the further distortion in the voltage. So this is the voltage for that. Okay. So you see, when the current is distorted because of this load, the voltage is also affected. Okay. And these are the consequences of the harmonics. A important consequence is basically the drawback of the presence of harmonic in the system. It results in the high rating neutral conductor, which causes overheating, effect on transformer and machines in terms of the poor performance. The requirement of power correcting devices such as the capacitors and their own implications, sometimes they won't work, the skin effect, losses in the motor, effects on meter. As you know that we use the meters to measure the powers, so they may also be affected because of the harmonics and unbalance. They may give erroneous reading if they are not well designed. This is an example of the neutral conductor overheating. As you see that since neutral carries the current, which is sum of the three-phase current, and this three-phase current normally, if it is balanced, becomes zero, but if it contains harmonic like third, fifth, so and so on, then you will see that the third harmonic or triplet harmonics, which are multiple of 3, like 3, 6, 9 and so on, they get added up, and which makes a very high magnitude for these triplet harmonics. This may cause the overrating of these conductors almost 240%, which is 3 times of the power conductor rating. As I said, these are normally measured with the help of the some index called TSD here or TDD defined as sigma I n squared n is equal to 2 to infinity and root of this. So basically this term is nothing but a kind of a harmonic content. This is IH actually, okay, this is IH, and IH by I1 is called the Ph.D, and IH by I is called the total demand distortion. The difference between these two is in the denominator. Here it is I1, here it is I, okay. Now you may ask question, well, that's fine, how do we control harmonics? Then there have been standard methods for this. The one is the most conventional, called tuned LC filter, which traps the desired harmonic component or the required harmonic component for which a filter is designed. And second option is to use active power filters. They are more adapting methods which can not only balance the unbalanced load but also can filter out any harmonic in the load side. Okay, we will discuss this more in detail in the coming lectures.